So let us move to theoretical approach for once again for a flat plate. Okay. So the governing equations are, you have continuity equation by dx dv by dy, that is equal to 0. U and v are the x component and the y component velocities, and then you have momentum equation, that will be u du by dx plus v du by dy, that is equal to, we said that dp by d0 can be approximated to 0. So we will have nu into d square u by dy square, okay. And then you have energy balance, that will be u dt by dx plus v dt by dy, that is equal to alpha into d square t by dy square, and the mass balance would be u dca by dx plus v dca by dy, that will be dab d square ca by dy square. Okay. So those are the governing equations. What are the boundary conditions? U is 0, okay, at y equal to 0, then so the boundary conditions are u at y equal to 0 is 0, u at y equal to infinity is u infinity, that is the free stream velocity, du by dy, we do not need that, we are happy with two boundary conditions on y. What about x? Which one? Yeah, but when you say du by dy at y equal to infinity is 0, what does it mean? It means that the velocity there has to be constant, and that has to be equal to u infinity, otherwise we do not have no acceleration fluid. No, but see, boundary conditions are not based on the solution that you would get. You have to use the correct boundary condition based on what is the physical problem. The solution comes later. You never write a boundary condition for finding a solution. You first find out what is the correct boundary condition and then you go and find a solution. That is not a correct approach. And then the other one is u at x equal to 0, what is it? U infinity or 0? So u at x equal to 0 inside the plate, so this is very important. Outside the plate it is obviously u infinity, but inside the plate what is it? By continuity, but that is not continuous at the edge of the plate. So remember what happens at the edge of the plate, the fluid suddenly comes to rest. Both the x component and the y component velocity are 0 in all directions, because the fluid is suddenly experiencing the flat plate, and so just inside the flat plate the fluid is come to complete rest at the boundary. So therefore u at x equal to 0 inside the plate has to be 0. You cannot be moving. If it is moving, then there is no meaning to have a plate here, okay, which means that it is a frictionless plate. Why? Right, but that is x equal to 0 at, sorry, that should be y equal to 0, that is right, that should be y equal to 0, that is the boundary condition, okay. So now obviously this is non-linear, look at the velocity equation, it is a non-linear equation and you will not be able to solve them analytically. But then there are some cute ways of reducing the equations to a form which is much more amenable to the standard analytical techniques, and that's given by what's called the method of Blasius. So Blasius is actually one of the very well known scientists who looked at these kinds of problems many years ago, and so he came up with this method to solve the, not actually solving and finding exact analytical solution, but at least there is a method to find the solution for the velocity profile and the and particularly to find the friction coefficient and the heat transport coefficient. Okay. So first one does not include, this is 0 at any x, right, but it is important to provide this boundary condition. You will see, because some of the transformations you make in this Blasius solution, you will actually see that it will account for both simultaneously. It's important to observe that this particular condition exists, that's all. Because when we started looking at flow past a plate, we said that the fluid suddenly comes to rest at that particular location. Okay. So if I say that you are indeed right in saying that if I simply say at all x this condition is automatically satisfied, which you will see has been actually used by Blasius in one of the approximations. So the way to use is called the stream function. So some of you must have I think most of you must have heard this word in your fluid mechanics class. So you say u is d psi by dy. So if psi is the stream function, okay, which describes the streamlines with which the fluid is moving, and v is minus d psi by dx. Okay. So the moment you assume this, the continuity equation is automatically satisfied, so we don't have to worry about the continuity equation. Then the most important observation that was made by Blasius is that the ratio of u by u infinity in the boundary layer, okay. So ratio of u by u infinity in the boundary layer is somehow a function of the ratio of the y by delta, where y is any y coordinate, the location in the y direction, and delta is the corresponding boundary layer thickness at that location. Okay. So if delta is the boundary layer thickness here, so what was observed was that the ratio of this velocity somehow has to be proportional to the location in the boundary layer. That's not hard to see now, but it was very hard to see at that time. Okay. Then he said, okay, so suppose we assume that we define a new function called eta, okay, which essentially sort of captures the effect of y by delta. Okay. So note that delta is a function of x position, delta is now function of the location. Depending upon where you are located, the height of the boundary layer is different. So you define a new quantity which is mu into x. Okay. So that's a new quantity. It's not by magic that he came up with this approximation. It is after several trial and errors he found that this is the correct scaling that you have to use. In fact, you will see in a short while why that's the correct scaling when we actually find out what is the boundary layer thickness at different locations. Okay. So you can actually see that there is, what is u infinity by nu into x? Any guess? What is u infinity by nu into x? So you can write this as, so u infinity by nu into x square root can be written as square root of Reynolds number, right? You can write it as square root of Reynolds number divided by x. Okay, so it has some functional form of Reynolds number, so that's nothing but square root of Reynolds number into y by x. So it's not a magic that he found this form, it's actually related to the Reynolds number, it's related to the properties of the fluid flow. Okay. Now in fact, you may recall that we said that Nusselt number has a certain functional form which is related to Reynolds number and Prandtl number. In fact, that functional form of Reynolds number comes from here. So you may recall that some of the expressions you may have seen in your, those who have done the experiments, you will see Reynolds number to the power of 1 by 2 that actually comes from here. We will actually see rigorously, we will derive and we will show that the functional form is Reynolds number to the power of 1 by 2, but I just wanted to mention that it comes from this approximation or this transformation that was started by Blasius. Okay. Alright, so from here you define another function called f, which is a function of eta, okay, and that's defined as psi u infinity into square root of. So that's the functional form for stream function. So you scale the stream function also with some form of Reynolds number, because Reynolds number captures the hydrodynamic conditions of the fluid flow. Okay. So from here we can find out what is u. So u is d psi by dy. So from here psi is u infinity into square root of nu x by u infinity into f. Okay. So f is now a function of eta, and so d psi by dy is u infinity into square root of nu x by u infinity, and I use chain rule, df by dy, df by d eta into dou eta by dou y. Okay. So all I have done is I am simply using the chain rule, okay, and d eta by dy you can get from here, that's nothing but d eta by dy, that is square root of u infinity by nu into x. Okay. So I can substitute that here, so that will be u infinity into df by d eta. So that provides an interesting functional form for the ratio. So you can see du by u infinity is nothing but df by d eta. Okay. So it's not that this functional form actually was got by magic, it was basically to come up with a very nice way of looking at the velocity profile and looking at temperature profile, which we will see shortly. Then we need to find v. V is minus d psi by dx, okay, and you can do all the chain rule business. So I'm not going to do the chain rule here. So that will be half square root of u infinity nu by x multiplied by eta df by d eta minus f. Okay. So I would like you, all of you, to do the chain rule and convince yourself that this is the correct expression for v in terms of the stream function. It's not very hard, it's just a couple of minute exercise. Okay. So now I can find out du by dx, I can find out du by dy, I can find out du by d square u by dy square. So if I know these three derivatives, I am now transformed all the components of the momentum balance. Okay. So the momentum balance will now turn out to be 2 d cube f by d eta cube plus f into d square f by d eta square, that is equal to 0, and df by d eta equal to 0, that is equal to f of 0, and df by d eta equal to 1. So that is the boundary condition. So momentum balance essentially reduces to this ordinary differential equation. What you had earlier was a PDE, which was a function of x and y, and now you crash it into an ODE, and note that you also had the x component and the y component velocity in the previous equation, but because you used a stream function formulation, so all that has been crashed into a simple ODE, third order ODE. Okay. F of, just write all the boundary conditions, you will see them. You can also bring actually another boundary condition for V. If you see that, you will actually get it. So, of course, it is non-linear. That's not a linear equation, and it's not a surprise. I mean, we are not going to get a linear equation from a non-linear equation anyway. So, it's a non-linear equation. It's non-linear in F. Okay. So, of course, these days you would be tempted to solve it numerically. But what Blasius did was he used a series solution. One could of course solve it numerically. You could of course solve it numerically, and so it has been, so he has worked out the, is now we have tables which gives you f df by d eta and d square f by d eta square. So now there are standard tables available for, again these tables did not come by magic, somebody has actually painstakingly worked out all these numbers for this differential equations, and so we now have tables which gives you these numbers. It's there in your text and it's also there in other references. So if you know these gradients, we are done. So remember that what we want really is to find du by dy at y equal to 0. That's what we want to find, right? That's what we want if you want to find the friction coefficient, because that's what we want to find. We are not interested in the whole profile. It's very boring to see the whole profile. So what is really of interest is to find the friction coefficient and the heat transport coefficient and mass transport coefficient. So if we know du by dy, we are done. So remember the expression for u by u infinity is df by d eta. So if you want du by dy, you need to know what is d square f by d eta square. So it's for that purpose the tables have been drawn in these three categories. Okay. Okay, so before we go into finding the friction coefficient, so we said u by u infinity is df by d eta. So what's the definition of boundary layer thickness? U tends to 0.99. So boundary layer thickness, that corresponds to the corresponding boundary layer thickness, right? And here it will be a function of eta, right? So whatever is the value of df by d eta at which it is equal to 0.99 tells you what is the corresponding boundary layer thickness, right? So it was found that when eta equal to 5, approximately 5, df by d eta was approximately 0.99. Okay, so that eta equal to 5 actually defines the boundary layer thickness. Okay, so it's the, so eta is given by y into square root of u infinity by nu into x, right? So boundary layer thickness is that y value for which eta is equal to 5. So therefore delta equal to y at eta equal to 5, that's given by 5 into square root of nu x by u infinity. What is square root of nu x by u infinity? It's x by square root of Reynolds number, right? So this is 5 into x by square root of the local Reynolds number defined based on the corresponding location. So the boundary layer thickness, now you've got an expression for boundary layer thickness as a function of the x coordinate. So that's very nice. So now you know, so supposing I want to find out what is the boundary layer thickness, I've got an expression to do that. As long as I know what the position is, I should be able to calculate what is the corresponding boundary layer thickness at that location. So that's an important piece of information. So remember, it's very difficult to measure experimentally what the boundary layer thickness is, but you've got an estimate now. You've got a theoretical estimate of what the boundary layer thickness has to be as a function of position. Okay, so with that, now we can go and find out what is the friction coefficient. So friction coefficient is defined as tau at y equal to 0 divided by rho u infinity square by 2, right. So that's the free stream, u infinity is the free stream velocity, and so that is mu into du by dy at y equal to 0 divided by rho u infinity square by 2. So now I can calculate it in terms of my modified variables, and so that will turn out to be, so that will be about 0.33, so it will be mu into u infinity square root of u infinity by mu x into d square f by d eta square at eta equal to 0 divided by rho u infinity square by 2. So if I know the second derivative of my function f with respect to eta, I am done. Okay. So that will be 0.664 into Reynolds number to the power of minus half. Okay. So that's the functional dependence of the friction coefficient on the Reynolds number. So that's the local friction coefficient, but what I am more interested is the average friction coefficient, because from experimental point of view, what I really require is the average quantity, and the local quantity is not of much use. So I can find out the average friction coefficient, which is given by the average shear stress at the boundary divided by rho u infinity square by 2, and so if you work out the integral, it's not very hard to do that. So that will be integral 0 to L 1 by L tau into dx divided by rho u infinity square by 2. So you can work out the integral. So that will be 2 times 0.664 into Reynolds number based on the length divided by 1 to the power of minus 1 by 2. Okay, and so that will be 1 point, how much is it? That's 1.328 minus 1 by 2. Okay, so that's interesting. So if I find the friction coefficient at length, okay, so that's the local friction coefficient at the end of the plate. Okay, so that will be 0.664 into Reynolds number based on the length of the plate to the power of minus 1 by 2. So that's interesting. So the average friction coefficient for the whole flat plate of length L is just the twice of the local friction coefficient at that location. So that's an important observation. Will be twice of the friction coefficient based on that length. Now there is some interesting thing you can actually extract from here. Suppose I want to find out, let us say I have another plate, okay, supposing I have a plate which is, I have done all my calculations and experiments based on a plate whose length is L, okay. Now if I want to repeat the same experiment, let us say half of the size, I don't need to redo the whole calculations. I can simply use this property in order to extract all the average quantities that I wanted to get. So if I know the local friction coefficient, then I should be able to estimate what is the average friction coefficient up to that location. So that's an important piece of observation.